So, hello and welcome to the seventh week of Advanced Algorithms. So, we are now in a phase of this course where we are going to be mostly talking about coping strategies for NP completeness, which is a concept that we introduced just in the previous week. So, last time we talked about all of these theoretical frameworks for intractability, demonstrating that certain problems are simply harder than others, and we don't really expect to solve them efficiently all the time. So that doesn't change the fact that these problems nonetheless need to be solved out there in the real world. So what we are going to do is see if we can relax some of our expectations from our algorithms and still get to some pretty good solutions as we go along for these so-called hard problems. Right. So just to recap, the kind of polynomial time algorithms that you have seen so far have a number of guarantees. So first of all, they're efficient in that if you look at their running time, it's usually capped at, well, not just polynomial. In fact, most examples we have seen are either linear time or quadratic or cubic. So it's not even some completely crazy polynomials. So we've had we've had the luxury of looking at some pretty good polynomial running times so far in the course. And apart from being efficient, they always get the job done correctly. So we've had the luxury also of correctness on all valid inputs. And this is kind of a big deal. This is one of the first things that we do when we analyze an approach to solving a problem, is that we really worry about showing that the algorithm is not just performant, but it also does the right thing all the time. So far, we've really had the luxury of working with problems that do admit algorithms of this sort, ones that are fast and that just work. And now we will be transitioning to discussing problems that are typically NP complete, where we won't have this kind of luxury, but we will spend our energies trying to figure out what are good sacrifices to make and what are interesting trade-offs and how can we still solve the problem in a meaningful way. So in this week, we are going to be focusing on the paradigm of approximation. And as the name suggests, we are going to give up a little bit on correctness, in that we may not always get to the optimal answer for optimization problems, and instead we will be happy with solutions that come with some sort of a guarantee of being sufficiently close to optimal, even if they're not exactly optimal. So we'll walk through a couple of examples of approximation algorithms in action, and hopefully these algorithms will be illustrative of some general principles, and hopefully it triggers your curiosity to go and find out more. And in fact, if you would like to do that, a great place to start is actually this book called The Design of Approximation Algorithms by Williamson and Schmois. It's freely available on the internet. You can look it up or find a link in the course notes or the course webpage. What we will be looking at this week is basically some glimpses from the early parts of this book. But of course, there's a lot more to find out. So think of this as some sort of a trailer to trigger your curiosity for more. And as a warm-up problem, let's get started with vertex cover. So let's begin with the definition. So the input to the problem is a graph G. And this is going to be a simple undirected graph. There are no edge or vertex weights to worry about. And let me just take a moment to define a vertex cover here. So a vertex cover is a subset of the vertex set of G, such that every edge has one of its endpoints inside S. Okay, so we want to say that for every edge UV in the edge set of the graph G, well, we have that S intersection UV is not empty, which is just a way of saying that every edge has at least one of its endpoints inside the set S. That's when S is called a vertex cover. Now, if you think about it a little bit, you'll realize that if S is a vertex cover, then G minus S, which is what is left if you remove the vertices in S, is actually an independent set. And well, why is that? Because remember from last week that an independent set is a subset of vertices which are mutually non-adjacent. So if I take any pair of vertices here, I claim that there is no edge between them. And that's indeed the case, because if there was an edge like that, then S is not a vertex cover, because we would expect at least one of these endpoints to actually be inside S. So G minus S is an independent set. So really a vertex cover is the complement of an independent set and vice versa, right? So if you can find an independent set, then you've also found a vertex cover. In fact, the complement of a maximum independent set would be a minimum vertex cover, and conversely. Now, what's the goal with the problem? Well, as you can imagine, we want to output vertex cover of the smallest size. And of course, there are different ways in which you could pose this problem. So the decision version of this question, if you want to think of this as a yes-no problem, as we have been thinking of problems when we discussed complexity classes last week. So the decision version would be that you also throw in a budget K, and then you say, well, you want a vertex cover not of the smallest size, but of size at most K. That would be the decision version. You would say yes if there exists a vertex cover of size at most K and no otherwise. You could also just turn this into a question about the size rather than the solution itself. The way I've written it right now, it's a search problem. You want to actually find a vertex cover of the smallest size, but instead you could simply ask for the size of any smallest vertex cover. And in fact, for the rest of this discussion, that's what I'm going to assume we are after. We want to find the size of a smallest vertex cover. And it turns out that our algorithms that find the size can also be adapted to actually also reporting the actual elements of the vertex cover. This is just like we said in dynamic programming. You usually report some sort of number corresponding to an optimal value, but if you want to find the set or whatever the solution concept is that witnesses that value, you can do it easily, usually by backtracking appropriately. So that's what's going to happen with our algorithms as well. So although I've written the problem as a search question, we will mostly focus on the optimization version of the problem, where we're just interested in knowing what is the value of an optimal vertex cover. And in this case, an optimal vertex cover is the smallest one. Notice that it does not make sense to maximize this value, because the set of all vertices in a graph is a trivial vertex cover. So it's intuitively, hopefully clear that what we want to do is find a smallest set of vertices that still operates as a functional vertex cover. Incidentally, there are graphs where you almost have to pick all the vertices, and that's the best you can do. So for example, if your graph is a complete graph, so every possible edge is present, then the value of opt is going to just be n minus 1 if the number of vertices is n, and that's because you just can't leave out more than one vertex from the vertex cover. Any pair of vertices that you try to leave out will form an edge. So there are graphs where the size of the vertex cover does go as far as n minus 1, and of course it can be as small as 0, which would happen, for instance, if your graph had no edges at all, right? So that's the range of the value that we are after. But let's think about how to come up with some sort of an approximation for the value of the smallest vertex cover. So we'll actually look at two approximation algorithms that give us the same guarantee, which kind of illustrate two different approximation strategies. So the first one here is going to be a more structural approach, where I'm going to try and look for a lower bound on opt, and this is something that's a good idea to look for in any case when we are doing approximations. So before actually going into what we will do, let me just spend some time explaining what I mean here when I say that finding lower bounds on the optimal is desirable. And these are lower bounds because we are trying to minimize a quantity. If you have an optimization problem that's a maximization question, then you would be looking for upper bounds. But why are such bounds relevant when you're trying to design approximation algorithms? Well, let's see. We're looking for a value that ranges between 0 and n minus 1, like we just discussed. We don't know exactly where this value lies. That's kind of the whole problem. But suppose we are able to establish that, well, no matter how small opt is, it can't be smaller than some value x, let's say. And usually coming up with such bounds is easier than coming up with an exact value. Of course, sometimes your bounds may be off by quite a bit. So it's possible that you're saying that opt is at least x. Actually, opt is in fact much bigger than x. But it doesn't matter. Let's say that you have hopefully a reasonable bound, which is x. Then you could focus on trying to come up with an algorithm whose output is, say, for instance, 2 times x. And then you know at this point that you actually have an approximate solution, because you know that whatever opt is, it cannot be smaller than x. Therefore, you cannot be off from the opt by a factor of more than 2, because you know that opt is at least x. Right? So coming up with some lower bound gives you sort of a concrete ambition to work with, and you say that, hey, if my output is not too far off from this bound, then we're good to go, right? So that's why coming up with these bounds is often a useful tool on the path to coming up with an approximation algorithm. So coming back to vertex cover, notice that we are trying to cover edges. So let's think about, what is a price that any solution needs to pay, including opt, right? Including the optimal solution that we are after. So since we're trying to cover edges, let's think about what happens when we look at a matching in the input graph G. So this is a collection of disjoint edges. By which I mean that no pair of edges share a vertex between them, right? And if you have a matching on, as we do here, if you have a matching on 5 edges, then notice that any vertex cover must be at least, do you want to take a moment and make a guess here? Feel free to pause the video. I wanted to say here that any vertex cover must have size at least 5, because the vertex cover has to worry about covering all of these edges. So each of these edges have at least one of their endpoints in the solution. And since there is no vertex that can handle more than one of these edges at the same time, each of these edges demands a separate spot in the solution. Now, we may not know which one of these endpoints must go into the solution, and it's of course also possible that the only way to cover all the edges in the graph is actually to pick more than 5 vertices. 5 vertices may not be enough. So by no means are we saying that this is a tight bound, because notice that I'm only giving you a certain set of edges that happen to be disjoint. The graph itself could have many other edges, right? But if you are looking at a collection of x many disjoint edges in the graph, then you know that opt is at least x for sure, right? Because there's really no working around this. You cannot get away with fewer than x vertices if you have a matching on x edges, right? Now, this is a great place to be because from here we can actually come up with a vertex cover whose size is 2 times the size of some matching. Okay, so which matching should we try to be working with? Well, notice that the bigger the matching, the better your lower bound. And in particular, there's nothing stopping us from working with a maximum sized matching, because it turns out that you can actually find a maximum sized matching quite efficiently in any graph. But we actually don't even need to invoke the black box of a maximum matching algorithm. It's actually enough to work with any maximal matching. So what is a maximal matching? Well, it's simply a matching which is stuck. You cannot add any more edges to this matching and still be a matching, essentially. So we can build a maximal matching greedily. We can start by picking our favorite edge, doesn't matter which one, and then you delete all the edges that are incident to either of the endpoints of this first chosen edge, E1. And then from the remaining graph, pick again whatever edge you like. I'm going to denote that as E2. And notice that E2 is going to be destroying from E1 simply because we got rid of anything that did have an overlap. And we keep repeating this process until, like I said earlier, we get stuck. So we build a collection of, let's say, some k edges which are mutually disjoint, and at this point we have, let's say, nothing else to pick from. The rest of the graph is empty, and we are done, right? So this is, let's say, a maximal collection of edges, and I claim that, well, of course we know that opt is at least k, because these k edges in particular form a matching. It may not necessarily be a maximum matching, so it's possible that you have a tighter bound by actually finding a maximum matching. But we'll see that as far as coming up with an approximation guarantee is concerned, it's not really going to matter, because, well, I'm going to give you a vertex cover right from this picture whose size is going to be at most 2 times k. And I want you to take a moment here to think about what this vertex cover looks like. There is a hint in the expression already. So the fact that the vertex cover has 2k vertices and this matching has 2k edges, maybe you already have some ideas. But if not immediately, then I'd encourage you to pause the video here and think about whether you can spot a vertex cover on at most 2k vertices. All right, I hope you had a chance to think about that, and I'm going to give this away at this point. So what I'm going to do is actually pick all the endpoints of all the edges in this maximal matching. So that's going to be 2k vertices, and well, that's hopefully the size of the vertex cover is evidently 2k because we have picked all the endpoints of k edges, and therefore that's 2k. But why is this a vertex cover, right? I want to argue that this actually forms a valid vertex cover in the graph. And the easiest way to argue this, in my opinion, is by contradictions. So we're going to say, well, suppose not. And then suppose we have an edge, both of whose endpoints are not accounted for by the chosen vertices. So in particular, let's say that there is an edge UV, which is left out by this proposed vertex cover, right? So UV, neither of those endpoints are covered by the chosen vertices, which are the endpoints of this maximal matching. But then notice that if this was indeed the case, then this edge is a perfectly solid candidate to be added to the maximal matching that we have just constructed. So we can extend our maximal matching with this edge UV, and the reason we can do that is because neither U nor V actually overlap with any of the vertices that we have seen so far as endpoints of the matching edges. That's just by our assumption that this edge is not covered by our proposed vertex cover. So recall how we built the maximal matching. We said we will successively pick edges and at every stage eliminate the other edges that overlap with the chosen edges. But clearly, neither you nor we were eliminated at any stage during our algorithm, because if they were, then that would not be an uncovered edge at this stage, but which means that the algorithm that built the maximal matching should really not have stopped at the edge ek, because at least there's one other edge that's still available. So if the set of vertices that's output by this algorithm does not form a vertex cover, then that contradicts the assumption that we were actually working with a maximal matching in the first place. That's a contradiction to the behavior of the algorithm. So that basically concludes our argument for the fact that the output is a valid vertex cover, and we've already seen that its size is twice the size of the matching that we are working with. And now we also know, as we argued in the beginning, that this is actually a lower bound for opt. So any vertex cover, including the optimal one in particular, must have at least k vertices, and therefore our output is basically off by 2. In fact, at most a factor of 2. Sometimes you might be lucky. It's possible that the optimal is much closer to the output of this algorithm compared to the ratio that we are claiming, but surely you're definitely not worse off than a factor of 2. So that's a valid bound. And of course, there are inputs on which it's really going to be as bad as twice opt. For instance, in a graph where the input is just a collection of disjoint edges, you would needlessly be choosing more than what you need. You can come up with more sophisticated examples to see that you actually hit this ratio on certain inputs, right? In any case, all this is to say that what we have now, based on this algorithm, is a 2 approximation for vertex cover. We call this a 2 approximation to emphasize the fact that the approximation ratio is 2. And this is an example of what we would generally call a constant factor approximation algorithm, which is basically to say that the approximation ratio does not depend on things like, say, the size of the input or the value of the optimal solution and things like that. It's sort of a universal constant. In this case, it's 2. Now, of course, whenever you come up with an algorithm, the standard question to ask is if you can do better. And in this case, it turns out that 2 is widely believed to be, again, some sort of a bottleneck, at least when it comes to the class of all graphs, and if you restrict yourself to polynomial time algorithms. Of course, if you relax either of those two assumptions, then perhaps you can do better. For example, famously, if you restrict yourself to bipartite graphs, then you can get the exact solution in polynomial time, because it turns out that on bipartite graphs, this lower bound of the size of a maximum matching is actually tight. You can always find a vertex cover whose size is exactly the size of a maximum matching if your graph happens to be bipartite. So that would be an example of relaxing the first kind of assumption. And of course, if you give yourself more time, if you can go beyond polynomial time, there might be interesting things you can do there, but that's going to be slightly out of scope for this current discussion. So having said that, now before moving on, I'd like to draw your attention to a couple of things. The first is to remind ourselves that, when we started off with this course, the first thing we talked about was the greedy paradigm. So as a fun puzzle or a little bit of food for thought, I'd like you to think about what does greedy look like for vertex cover. Well, notice that we now don't really have an obligation to be correct necessarily. We just have to be within reason, close to optimal, right? So what would be a natural greedy algorithm for vertex cover? Remember that we are trying to pick a smallest number of vertices to cover all the edges in a graph. So the greedy strategy might be to choose vertices that happen to cover a lot of edges. And if you think about it, that would naturally turn out to be vertices that have high degrees. So you could, for example, sort the vertices according to their degree in descending order and prioritize vertices that have high degree. It does feel like vertices that have high degree basically take care of a lot of edges in one shot, and they're perhaps more deserving of a spot in a vertex cover of small size. So it's a nice question to think about what's the performance of this greedy algorithm, not in terms of running time, it's evidently a polynomial time thing to do, but in terms of how close it gets to the optimal solution. Think about arguments, but also think about examples. Can you come up with scenarios where you can basically trick this algorithm into producing a vertex cover that's much larger than the optimal one? So that's one question that I wanted to leave you with. And the other thing I wanted to say is basically leading up to the next video in this series this week. So we'll continue talking about vertex cover, and although we won't necessarily come up with a better approximation ratio, we will basically see a different approach to coming up with a 2 approximation, and that'll be using the method of rounding a solution to a linear program. So you've perhaps seen linear programs before, so it would be a good idea to recap the basics if you feel like you don't remember them completely. We will try to keep our discussion as self-contained as possible, but nevertheless, if you have seen them before and you would like a recap, that would be a nice thing to do ahead of the next video, where we will be talking about a LP formulation for the vertex cover problem and how that in turn leads to a 2 approximation.